We've now discussed temperature enough that we can accurately measure the temperature of something. So the next, we need to discuss the concept of heat. Heat is also central to the topic of thermodynamics, but in this case the colloquial definition of heat and the scientific definition are a little bit different. Heat involves the flow of thermal energy and is distinct from the temperature of an object. If we take a can out of the refrigerator and put it on the table, the temperature of the can will increase gradually until it reaches room temperature. In the same way, if we pour a cup of coffee and put it on the table, it will cool down until it reaches room temperature. So, to generalize, we call the soda or the coffee a system, and we consider the room to be the environment. So what we will see is that if the temperature of the system, so the drinks we're looking at, is not equal to the temperature of the environment, the room temperature, then the temperature of the system will change. The temperature of the system, our drinks, is related to the internal energy of the system. That means when the temperature increases, energy must be added to the cold can of soda, and if the temperature decreases, then energy must leave the hot coffee and move to the environment. This transfer of internal energy is called heat, and it's symbolized by the letter Q. So heat is the flow of internal energy to and from a system. Heat is positive when the environment transfers internal energy to our system, so like the cold soda when it's warming up, and the heat is negative when internal energy flows from our system to the environment, like when the hot cup of coffee cools down. So if the temperature of the environment is greater than the system, then the heat will be positive. If the temperature of the environment is less than the system, then it will be negative. If we put our cup of hot coffee into an even hotter oven, then internal energy will flow to the cup of coffee. So the heat is not really the temperature, but it's related to how the temperature of our system compares to the environment around it. So heat is the energy that is transferred between a system and its environment because of a temperature difference that exists between the two. So there are a number of ways that heat can flow between two objects at different temperatures. Heat can flow through conduction, where if two objects are in direct contact with each other, they can rapidly reach the same temperature. Or, for example, if you have gas molecules, they can collide with our cup of coffee, cooling down the coffee. We also have convection, so the flow of fluids can lead to heating or cooling because the hot or cold molecules themselves can move. I always imagine here that you're holding your hand directly above a candle. You'll notice that your hand gets really hot very quickly because the hot air that is inside of the flame rises, runs into your hand, and it's kind of painful. While if you hold your hand to the side of the candle, you feel a bit of warmth, but it's not particularly painful. We also have radiative heat transfer, in which the electromagnetic radiation flows from one object to another due to their blackbody radiation. Here, think about the sun warming the Earth through electromagnetic rays it emits, or the cooling of the Earth through the emission of infrared electromagnetic radiation. So, now we want to think about heat a little more quantitatively. The units of heat is the units of energy, so joules or calories are commonly used as well. I guess there's BTUs as well, but we're not going to worry about that. So joule is the standard SI unit of heat, but calories are a very popular unit, so with 1 calorie being equal to 4.184 joules, and 1 kilocalorie being equal to 4,184 joules. Notice the units for dietary calorie is the kilocalorie, which is the 4,184 joules. The heat capacity of an object is the proportionality constant between the amount of heat and the change in temperature that this amount of heat produces. Usually we will use the specific heat capacity, which is the heat capacity per unit mass of a substance. So the heat Q will be equal to the specific heat capacity times the mass of the object times the change in the temperature. The term capacity is a bit misleading because there is no maximum value of heat that an object cannot take. You can always heat something to a higher temperature. Rather, it's a measure of how easily the temperature of something can change. A large heat capacity means that it takes a lot of heat to raise the temperature of something, and if its temperature goes down, then it releases a lot of thermal energy as it cools down. Something with a small heat capacity, on the other hand, will see its temperature increase by a lot when a little bit of heat is applied to it, and if it cools down, only a little bit of heat will be released to the environment. So the specific heat capacity is marked by the lowercase letter c, and it has units of either joules per gram Celsius or units of calories per gram Celsius, so depending on which unit of heat we want to use. This does assume that there are no phase changes, and notice that if heat Q is positive, then the temperature increases, and if heat is negative, then the temperature decreases. So I guess we can do a quick example. A can of water that weighs 350 grams warms up by 10 degrees Celsius. So the question is, how much heat was required to raise the temperature? Well, we use our formula for heat. Q is equal to the specific heat capacity times the mass times the change in temperature. So the heat capacity of water is 1 calorie per gram Celsius. So we multiply the heat capacity times the mass, 350 grams, times the change in temperature, which is 10 degrees, and this gives us 3,500 calories, or 3.5 kilocalories, to raise the temperature of this can of water by 10 degrees Celsius. So one way in which the internal energy of a system can change is through heat. Another way that a system's internal energy can change is when it does work. So how can a system do work? Well, imagine we have a balloon, and the pressure inside of the balloon is larger than the pressure outside. If that happens, the balloon will expand until the pressure inside and outside is the same. So when the balloon expands, whether it's through adding more gas by blowing into it or by heating it, the balloon does work pushing against the atmosphere that's pushing against the balloon. To be more quantitative about this, work, you'll remember from way back when, is the force times the displacement. The displacement of a piston is the volume of the piston divided by the area of the piston. So the work is equal to the force divided by the area times the volume. Notice force divided by area is the pressure, so we can say the work done is equal to the pressure times the change in volume. This should make sense. If the volume increases, then the system has done work, and if the volume gets smaller, then work has been done to the system. So to see how the work is done by a system, we're going to graph the pressure and the volume of the system and see how it changes. The graphs here are what are called PV graphs, and the y-axis is the pressure of the system, and the x-axis is the volume. So there are a number of processes that can happen to a gas where its pressure and volumes change, but for the moment we just want to focus on the work done. The area under the curve in a pressure-volume graph is the work done. However, you have to be careful about the sign. If the volume of the system has increased, then that means that the system has done work, so the work is positive. If the volume of the system has decreased, then the environment has done work to the gas, so the work in this case is negative. Look at the graph to the right here. So on the top we have an isothermal expansion in which the volume increases as shown by the blue arrow, and the pressure decreases in a smooth curve. In this process, the volume has increased, so the gas has done work, the work is positive. On the lower graph, we have the reverse process where the gas is compressed, shown by the red arrow. And because the volume has decreased, work is done by the system, so the work is negative. Notice that if the pressure is zero outside of the system, if that pressure is zero, then the work done is zero, and that if the change in the volume is zero, then the work done is also zero. The direction of the arrow is critical to whether work is done by the system or whether work is done to the system. Notice if the system does work, it has lost internal energy. Either the temperature has decreased or heat has been added, internal energy to the system to balance things out. If work done is negative, then work is done to the system, then the internal energy of the system will increase, although again, a heat flow can also occur at the same time. Notice the work done depends on the path of the system. So how you get from one value of pressure to volume can cause a different amount of work can be done here. In this case, we've just shown two that are the same shape, but we can take any path from our initial to final pressure and volume, and with a different shape, you'll have a different amount of work done. So this brings us to the first law of thermodynamics. So work and heat are both dependent. If you travel from one value of pressure and volume to another, you don't really know how much work is done. You need the area under the curve, so you need to know the pressure and the volume at each intermediate point along the curve to know the change in work and heat. However, if we measure the heat minus the work, that value is constant no matter what path we take. It only depends on the initial and final conditions. This value, heat minus work, or Q minus W, is the internal energy of the system, so the change in internal energy U is equal to the heat minus the work done by the system. This should sort of make sense, so heat will add internal energy to the system, and the system doing work will remove internal energy from the system. This equality is pretty much the same thing as the first law of thermodynamics. So way back in 201, we talked about energy conservation in isolated systems where energy cannot enter or leave. This first law of thermodynamics is an extension of conservation of energy into systems that are not isolated. So this first law tells us that energy may be transferred through the system boundary, either through heat or through work. So the first law of thermodynamics is a form of conservation of energy that works for the internal energy of a system. Okay, you guys have a few questions to answer. Most of these should be pretty straightforward. Sometimes heat capacity gives some people some problems, so good luck.